This video is about voltage. It corresponds to section 4.1 of the Applied Analog Electronics textbook. Now, from a physics standpoint, a voltage is a difference in electrical potential between 2 points in space. But in this class, we're not going to be going much into electric fields and the physics of how electricity works. That's what physics classes are for. And the only thing that we really need to be sort of constantly aware of is that a voltage is always a difference between two, here they said points in space for physics, we'll actually be looking at as differences between two nodes. What is a node? Well, a node is a mathematical abstraction, and it is an abstraction of a wire, and we'll draw it on a schematic diagram as just a line. And what we're going to say is that every point on this line has got the same potential. It's the same level in the field, so the voltage difference between any 2 points on the line is 0. We can have another line and say that's a different node, and the idea again is that every point on this line is at exactly the same voltage, but it's a different voltage from this other one. So if I call this line A and this line B, we will talk about VAB as the voltage between A and B, the difference in potential from A and B. Okay, now I've drawn these nodes as lines on a piece of paper here, and a lot of people will think of these lines as wires. And that's not too bad a way of thinking about them, because a wire, piece of metal that conducts electricity well, if you put a voltage on it at one point in a wire, then all the places on the wire are going to have about the same voltage. And we can treat it as if the wire was a node. The wire is a real physical object. The node is a mathematical concept. Mathematical concept being that the potential is the same at every place along that node. When we're drawing schematics, incidentally, if we draw two lines crossing like this, they're not connected. They have possibly different potentials. There can be a voltage difference between those two lines. If we wanted to draw two lines crossing and say that they are connected, we have to put a connection dot. So these are connected. Now there is a convention that if you draw a T connection like this, that it means a connection. But that can be kind of ambiguous because sloppy drawing like that, were those supposed to be connected and it just went too far? Or were they not supposed to be connected and it just hasn't finished drawing the line? Confusing. So it's a good idea to always put the dot there so that the connection is always clear. Okay, said that voltage is always a difference between two nodes. We said previously points in space, but in this class we're always going to be dealing with nodes on a circuit. What we often end up doing, however, is choosing one node out of our circuit and saying, let's call this point 0. So we draw that with a special symbol like this, and we call it ground. And by definition, ground is 0 volts. So now if we want to say, what is the voltage between A and ground, or what is the voltage between B and ground, we can just write V sub A, V sub B, to leaving out that it's with respect to ground. If you only give one node for a voltage, the other one is always this special node ground, which is just an arbitrarily chosen point in our circuit, an arbitrarily chosen node. Now, one thing you may notice here is that I've got two different ways of talking about the voltage between these two wires, because I can talk about it as VAB. I can also talk about it as VA minus VB. And this is due to a nice property of voltages, and that is that they're additive. If you have the voltage at A to ground, the voltage at B to ground, the difference between them is the difference voltage A minus voltage B. If you take any sequence of nodes, go around in a circle and go from voltage A to voltage B to voltage C, go all the way around, the voltage differences across each pair of nodes, when you add up and come all the way back to where you started, they all add up to 0. That's known as Kirchhoff's voltage law. And the only thing we'll use Kirchhoff's voltage law really for is the fact that it allows us to talk about the voltage at a node by having picked just one arbitrary node as being saying that's 0. And the consequence of that is we can do what's called nodal analysis that allows us to talk about voltage at a single node. Okay, now I said stuff about going around a cycle and all that sort of stuff. There's another thing besides nodes that we're going to have in all our schematics, and that's components. We can have a node here called A, we can have a component here, another node called B. We'll have voltage across AB. We'll sometimes talk about that as being the voltage across this component, and it's always across a component for voltage. And that's the difference between the two ends, and you do have to worry a little bit about which end is which when you're talking about across the component. So we'll nearly always be using a notation like this one where we have voltage A, B for voltage A minus voltage B. Or sometimes we'll actually write it out explicitly as VA minus VB. We can connect components in various ways. For instance, we can have another component on the same node B and connect this other end to node C. And we now have a very simple property of this, and that is that VAB plus VBC is VAC. Voltage across this component plus the voltage across this component is the voltage across the pair. And if you write it out as this difference, VA minus VB plus VB minus VC, you can see that the plus VB minus VB cancel, and you get that this is VA minus VC, which is exactly what VAC means. Okay, so this sort of connection is known as a series connection. And the property of series connections is that the voltages add. We have another common connection that we'll often see in circuits, and that is where we have the component and another one connected up to the same pair of nodes. And here, the voltage across this component, let's say this is component 1 and this is component 2, the voltage across component 1 is the same as the voltage across component 2. They're both VAB. So when you connect components in parallels, the voltages stay the same, and when you can connect components in series, the voltages add. And that's basically all the properties of voltage that you will need until we start introducing more concepts that will need the relationship between the voltage and those other concepts. But for now, that's enough.